Combination circuits, resistor and capacitor. When combining the resistor and the capacitor in series, we find that as a series circuit, the resistor and the capacitor, when connected to the supply at a certain frequency, will allow the same amount of current to flow through the circuit. The voltage will be divided across the resistor and the capacitor. Because the capacitor is reactive in nature, a lagging voltage in the supply with reference to the current. Looking at the phasor diagrams, the resistor's voltage is in phase with the supply current, and the capacitor will have the supply current, and then the capacitance will be lagging by 90 degrees. The result when combining these two, current being my reference as a series circuit, we will have the resistor voltage in phase with that current, and we will have the capacitor voltage lagging that current by 90 degrees, and the result on the supply is the 90 degree or the lagging, somewhere between 90 and 0 degrees. The impedance of this circuit is the same as the impedance of a inductor resistor circuit, where we've got the resistance on the horizontal, the capacitance on the capacitive reactance, on the vertical, pointing downwards or lagging by 90 degrees, and then the resultant impedance or the total opposition to the flow of current in this circuit will then also be lagging, the same as with the inductor resistor circuit. However, it is a lagging factor. When calculating the voltages over the resistor and the capacitor, VR equals I times R. For the capacitor, VC equals I times XC, capacitive reactance. And when we get to the total voltage calculation, V total equals the square root of VR squared plus VC squared, and all of that rooted. When it comes to the impedance calculation, Z is equal to R squared plus XC squared. When connecting the components in parallel, our capacitor connects to the resistor, and that connects in parallel to my total voltage. Total voltage now becomes the reference because it's the same on both components, and we find again that current and through the resistor and current through the capacitor will be determined by their individual reactances or resistances, or the ohmic value. So looking at these two configurations, in the resistor, remember, everything is in phase with each other. resistor's current versus the supply voltage, and then the supply voltage on the capacitor. But now we will have a leading current because of the phase shifting capabilities of the capacitor. When combining these two aspects, voltage is the reference, the resistor current versus the capacitor current, and when combining those two, again we get the total current, which combines and serves as my supply current. Now see that the current is leading the voltage, or the voltage is lagging the current. That is due to the effects of the capacitors charging and discharging, which we call the capacitive reactance. When calculating the impedance, inverse of impedance equals the square root of the inverse of the resistance squared plus the inverse of the capacitive reactance squared, which gives me my impedance. Total current, I total, is equal to resistor current squared plus the capacitor current squared, and then all of that rooted. But again, like we had with the inductor, calculating the impedance is always easier just using Ohm's law, total voltage divided by total current.